Alright, let's start again. I still haven't uploaded the previous one, but I wanna start. I think I wanna try to get to 75 or 77 today. Because that way I can finish the other ones in between 3 or 5 hours tomorrow. And I can start studying topic by topic tomorrow already. Because I feel like it might be just enough already from all these problems. So at this point, I'm just trying to finish them really fast so I can start studying the previous ones more in depth. Given an integer array nums, find a contiguous subarray containing at least one number which has the largest sum and returns its sum. Containing at least one number which has the largest sum and returns its sum. So isn't that really the same thing as the product one? What's the difference here? I already forgot the product one as well. I think it was a bottom-up one from dynamic programming. Yeah, there was one for the negative values and another one for the... Honestly, I think I'm gonna look at the solution from the previous one and try to adapt to this one. I think it might be a better thing to do. Maximum product array was this one.
Hey everyone, welcome
Remember
back.
there was a
write some more
negative and a positive value they kept track of. And this here.
In that case, this is our max product, which is even less than 0. So 0 is not a good default case. And I'm going to maintain the current min and the current max, and I'm going to initialize these to 1 each because we know 1 is like a neutral value. And then we're just going to start iterating through every single number in our input array. We know that if we ever get to a 0, we do not want to handle that. We don't want to add that as a part of our product. So we don't want to mess up our current min and max by multiplying it by 0 because then it's going to stay 0 forever. So instead, what we're going to do is we're going to reset our min and our max to 1 each, and we're just going to continue to the next iteration of the loop. If this doesn't execute, that's when we're going to actually do our code and recompute the current min and current max. So our current max, how are we actually going to compute it? Well, in Python, it's really convenient for us because we can say, okay, the current max could potentially be the new number that we just found multiplied by the current max. If the current max happens to be positive and n is positive, it could also end up being the input value n multiplied by the current minimum, right? What if n is negative and current minimum is negative? Then this could end up being a positive number, which could be our current maximum. The third option is n itself, because what if we had an input such as -1 and 8? Well, in that case, the current min and max is going to end up being -1, and either of those numbers multiplied by 8, which could be our hypothetical n value, is going to end up being -8. So 8 it's by itself, which is n, is the maximum. And the fun thing about Python is that, look, we just put 3 values into our max function. Some languages don't allow for this, but there's obviously ways to get around it. And so now that we have our current max, we can do the exact same thing for our current min. So min. So we can actually take all 3 of these values, copy and paste them, and then put them in the min because we want whatever the min containing n is, and it could be anything. It could be n times current max, n times current min, or n itself. So an example would be -1 and -8. If we multiply these together, we get a +8, but we don't want that. We want the minimum, which could be just -8 by itself, which would be this third case. But this is where I always end up with a bug. So do you see how we actually recomputed the current max, but we want to use the old current max? So I'm actually going to have a temporary variable up here, temp, and before we end up reassigning current max, I'm just going to compute current max times n and then save it in temp so then we can use it down here. So we're going to replace this with temp. So this way we're always keeping track of what the current max is and what the current minimum is, and so we can update our result after each iteration of the loop, and we want the max product, so we can take the maximum of result itself, because result could still be the max, current max, and current minimum. So that's actually it. Like, we've done it, and we can now just return what our result is. And so this is actually not that much code, and it's not even, like, when you look at it, it's hard to recognize that it's even a dynamic programming problem, because it's not like we're storing an entire array like BP and then having an array. We're just maintaining 2 values, current min and current max, and what they tell us is, for, let's say, for example, we were at this value, n, then we're going to have the current maximum of this subarray and the current minimum product of this subarray. And then when our n gets shifted to the next value, we're going to have the current maximum of these 3 and the current minimum product of these 3. And then by the time our n value is out of bounds, we will have the current max and the current minimum of the entire array computed. So it runs efficiently, and that's because we're only iterating through the input. So instead of being n squared, the time complexity is just big O of n. The memory complexity is big O of 1 because we are not using an array. We're just using single variables. I hope this was helpful. If you enjoyed, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon.
What the hell, man? It's supposed to be the same thing. For maximum, minimum. Let me see how many I'm getting wrong. Just see how often we still have. So probably there's something fundamentally wrong here. I need to get the maximum sum, I think. Output 24, here I'm getting 23. So maybe it's because I start at 0. 0, 0. Three and 5. Huh. I feel like this shouldn't be an easy as well, if it is roughly the same level of difficulty as the other one. Because it's pretty much the same problem, but this one is summing and the other one is multiplying. And the other one is a medium problem, so. Return its sum. Oh, so I need to return the sum. That's what I'm doing wrong here. I think. Because I'm returning the other one was supposed to return the product. This one is the sum of the array. Oh no, actually it's pretty much the same thing. So current max, current minimum. Looping through nums, if n equals 0. Oh, maybe it's this condition here. So let me erase this one. Still think it's not gonna work, but maybe helpful. Oh, there we go. So that was the only thing. Yeah. So let me look at the solution. It's probably gonna be the same thing, actually.
Let's solve LeetCode 53 maximum subarray. So we're given an integer array of nums, and we want to find the contiguous subarray containing at least one number which has the largest sum, and then we want to return only the sum. So this array has positive numbers and it has negative numbers. So that's what we have to keep in mind. In this case, the largest sum is 6, and it's just this middle portion of the array. So the first thing you might try is just compute every single subarray, right? So let's first compute every single subarray starting at -2. There's one subarray, there's two subarrays, there's three subarrays, and then we keep doing that until we got to the end, right? And then we could repeat the process for the second number. So the subarray starting at 1 here, another subarray starting at 1 here, another subarray starting at 1 here, all the way until the end. Now we could repeat that same process for every number in the array. So let's just write the pseudocode to see what kind of complexity this would yield. So let's say we're starting, the I is going to represent the starting value. It's going to range from 0 all the way to the last number, n-1, or the last index, n-1. And then we want to get the ending index. So I'm going to use j for the end of this subarray. So we're going to start at I, and we're going to keep going until the end of the subarray, or until the end of the entire array, n-1. So this represents the start, I represents the start, j represents the end. Now we actually want to compute the sum of this subarray, so we're going to have a third loop for that, right? Let's use k. K is going to range all the way from I to j, right? Because that's what represents the subarray. And then in here we compute the sum, right? Now, obviously, this is really inefficient, right? The time complexity is n cubed. It's obvious because we have three for loops. So let's try to expand upon this. Let's see if we can make any shortcuts to improve it. So the most obvious thing you'll probably notice is that we can save time when we're computing a subarray. So if let's say we computed this subarray, right? And then we want to compute the next subarray with just one added element. Well, we can save the result of this, right? And say it's our current sum or whatever. And then to compute this subarray, we just have to add this number over here, right? So we can just say current sum plus -1. And so this can save us time. Let's take a look at the time complexity of this solution. So we're going to have another for loop, which is going to represent the start. So start is going to range from 0 all the way to n-1. And we're going to have another loop for the end of the subarray. J is going to range from I to the last index, n-1. And then inside the loop, we're going to maintain our current sum and simply just add the number j each iteration of the loop, right? So this is a little more efficient, O of n squared. It's a pretty easy optimization to make, and it improves your solution a lot. But can we do even better than this? So now the question you should ask yourself is, do we have to compute every subarray starting at every single value in the array, right? Do we have to start at every single value and compute every subarray that comes after it? I don't think we do. Remember, we're trying to find the maximum subarray. We can use that knowledge to help us make a shortcut. So let's take a look at this. We have a -2, right? So when we're starting here, that's going to be our max sum so far. Then we get to -2 plus 1. So this is -1 so far, right? Do we actually need this negative number? The negative numbers don't contribute anything in this case, right? So we can basically ignore that value, right? Once we get here, we can basically say this negative value, this negative prefix that came before +1 isn't going to help us at all. So let's not even consider it. So next we get to this -3. Now up until here, our total sum is -2, right? So then we get to this 4. This is a negative prefix that came before it, -2, right? So we can say up until this point, we're not even going to consider what came before. So this 1 and -3 aren't going to help us at all. Just ignore them. Now we get to a -1. So the prefix that came before this was a +4. So we're going to not delete it from our list. We're going to keep that +4 and add it to this -1. So now we're going to be at 3 so far. Now we get to a +2, right? Even though there's a -1 that came before it, well, there was a +4 that came before that. So if we get rid of this -1, we also have to get rid of the +4, which we don't want to do. Remember, we have to keep the subarray contiguous. So I'm not going to chop this portion off. I'm going to keep it. Now we're going to add 2 to it. So now we're going to be at 5. Then we're going to get this 1. We're going to add it and get our subarray of 6. And this is the result so far, but let's keep going and see what happens. Next, we'll have a -5, right? So -5, now we're at 1. So obviously, we decreased our subarray, but we know this -5 is not going to be deleted because we had a +6 portion comprised of these 4 elements that came before that. Lastly, we get a +4 again, add that. Our sum is still 5, so we see that the max subarray was this portion of these 4 elements, which totaled to 6. Now, this was a linear time algorithm. It's kind of like a sliding window, right? We keep incrementing our right pointer as we go through the array, right? But our left pointer keeps getting shifted if we ever have a negative prefix like this -2 or this -2 portion comprised of these 2 elements. So anytime we get a negative prefix, we remove it. And for me, it kind of helps me to think about this as like a sliding window. And since it's a linear time algorithm, the overall time complexity is big O of n. We didn't need any extra memory. We just had to go through the array, removing any negative prefix as we computed the total sum. Okay, so now let's code it up. So we can initialize our max subarray to the first value in the array. That's like the default value that we're going to give it because we have to give it something, and it can't be 0 because we know we have negative values in this array. And we know the array is non-empty, so the 0th value of the array is always going to exist. And we're going to be constantly computing our current sum, so I'm going to initialize that to 0. So let's go through each number in nums. Now remember, if we had a negative prefix, we're going to remove that portion from our current sum. So the way that we can check this is just check if current sum is at any point negative. If it's less than 0, we're just going to reset it back to 0. And then after that, we can add our current number to this. This will make sure that we're always computing the maximum that we can. Now, this current sum could be the possible maximum, so we're just going to update our max subarray to the maximum of itself, as well as the max that we just computed. After we're done with that, we'll return whatever we computed as the max subarray. I hope this helps show you kind of the intuition behind the solution of this problem. If it was helpful, leave a like and subscribe, and thank you for watching.
The reason why this is easy and the other one is hard is that this one you can get rid of the negative values, and also you don't need to concern yourself with the 0. So I think it makes sense, but I still think it should be. Maybe not. Maybe it is an easy one. Or maybe some of these problems are harder for me because I'm not really thinking about them from strictly trying to solve, but trying to implement the stuff that I'm learning. So it might be one of the reasons why it might be harder for me, because I'm thinking about the other problems that I just went through and how I can incorporate the stuff that I learned from them into these other problems instead of thinking about it from scratch in the same way that I would solve before I started doing these LeetCode challenges, because I would probably solve it in a completely different way back then. Then what I'm trying to do here. You're given an integer array nums. You are initially positioned at the array's first index. Each element in the array represents your maximum jump length at the position. Return true if you can reach the last index, or false otherwise. Jump 1 step from index 0 to 1, then 3 steps to the last index. Even an integer array nums are initially positioned at the array's first index. Each element in the array represents your maximum jump length at that position. You always arrive at index 3, no matter what. Oh, okay. So maximum jump length is 0, which makes it impossible to reach the last index. So pretty much it's only impossible if there's 0 before, I think. Because then, unfortunate thing is that I couldn't get any pattern from the previous one about this greedy way to solve things. I don't know if it's a data structure or if it's a method, this topic here, to solve. So let's think. So what's the decision here? I think the decision, the index that you are located is the one that's going to determine how many you should look ahead from that index. And then from the ones, if there is one that is reachable from the one that you are ahead. So for example, let's say if you are on this one, you should look at the two next ones and see if they're bigger than this one and which one is the biggest. So in this case it's 3, and then you select, because it's 3, you select the biggest and go to that case, and then you do that recursively until you get to the end. But then the problem is this might lead you to a 0 in some situations. So that's the issue, because then you would have to do the check recursively to see if you're gonna fall into a 0. So how can I say if there's a 0 after the final check? Do something else, or go back to the previous one. Yeah, I think this approach is not the best, probably. I can't think about an easy way to write that. To decide which squares I'm gonna jump. It's kind of similar to the problem with the steps, where you have a stair and then you need to see all the combinations of steps. You can jump one step or two at a time in the stair, and then you need to figure out all the combinations. It's kind of a similar problem. And this one feels a little bit more difficult than the other one. Can't I just look at the 0? The indexes of the 0? Because that would be the easiest solution. So I put this. And then I go from here. So I pretty much have to avoid the zeros. Or maybe I can do some logic like the sliding window, but reverse. Yeah, maybe that's a better approach. So I start for the end, prime range. If nums -1, -1, -1. If nums I equals 0, then I count something. Because if it's 0, I want to know if there's one that skips the 0. But how can I know that? I need to get the difference in the indexes from yeah, I can make j equals 0 here and j plus equals 1. Or, well, let me think. Because I need to find one number, and the first index is also important, that's the thing. So maybe one condition I can put here is if nums 0, or if num 0 is equal to 0. So I'm pretty much saying if the index of the next one is equal to 0, return false. And that takes care of this case here, where you have 3 and we're gonna directly jump into 0. And then here I want to check for any zeros if maybe we should do the other way around, where I assign the variable here and then I make it equal to 0 here again. And outside I make it like this. Because when it reaches the 0, because it's going from right to left, I want to know if there's an element where the difference is going to be greater than the index of the 0. So pretty much if j nums j, but that's not the same. Let me think. Or maybe I don't need j. I can use the length of the nums minus j, minus I. Yeah, length minus I is gonna be the index of the number. But how I'm gonna keep track of that? Because I'm thinking I'm going from the right to left here, so let's say I'm here, then I go here. Once I reach the 0, I wanna see if there's any number here on this side that the value of the number allows me to jump through the 0. And if the answer is yes, then I can probably get to the end. But then the other issue is that I have to check if there's another element that allows me to get to that element, and that's the problem. So the value of the cell, let's say, determines the size of the subarray. So maybe what I can do is calculate the subarray. Instead, I can move normally from left to right and then use the value to calculate the sum of the subarray. To calculate if there's 0 in the subarray. And by that still, because the issue is you can jump less than the maximum and get you another square that jump allows you to jump through the 0. Oh, but maybe I can eliminate that. So let's say here is 2, then I can go either to 3 or 1, which is the size of the subarray. And if I see there is a 0 here instead of a 1, that means I can remove this element, remove the 2, decrease the 2 by 1, and then check again. And then if this was a 1, then it would mean that I would return false. And if it's not, if it's a different value, then I do the same calculation again. How would I have the subarray? How would I make that? Maybe I can make like this. Length nums I. But it wouldn't be the values, that's the problem. And what if I make nums equals to that? So nums. Yeah, I don't think this is the best way to go about it, probably. as I'm thinking about getting the value and then doing what I just talked about, where I check if it's gonna be a 0, then if it is, I subtract to see if the next elements are gonna be a 0 or not, but it doesn't feel like it's the correct approach for this. I just think if there's a different way to think about the problem. It's almost at the end, so I think I'm gonna look at the solution.
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve a very popular problem and probably one of my favorite problems of all time. It's jump game. So this is a very popular dynamic programming problem, but it can also be solved in a greedy way. I'm going to show you both solutions and then we're going to code up the greedy solution, and it's very little code, so that's the good thing, but it's a pretty clever problem. So let's dive into it. So we're given an array of non-negative numbers, so all of them are going to be 0 or positive, and we're initially positioned at the first index of the array. So for example, in this input array, we're positioned at the first index or the 0th index, right? The first position. So this is where we're going to start. We're going to start in this position. And so for every value in the array, for every element, the number itself, for example, number 2 in the first position, represents the max jump length that we can perform at every single position. Basically what that means is from this first position, we can only do a max jump of 2, meaning our max jump can only get us to this position, right? And another example, from here, since this is a 1 value, the max jump we can do is a 1 jump, meaning we can only jump to the next position, right? Obviously this is a 3, the max jump we can do is a 3, meaning we can reach the end position, the 4, from here, right? Because we can do a jump of length 3. Given all of that, given that we're positioned here and that every value represents the jump size, we are only asked, can we reach the last index? So starting from here, given these jump values, are we able to reach the destination, which is the last value in the array? So in this first example, the answer is yes. So we return true because yes, we can reach this position. How can we do it? Well, we start here, so we can do a jump of length 2, or we can do a jump of length 1, right? We don't have to do the max jump length. We can choose to do 1 jump. So then let's say we're at the second position now, right? So now we're at 3. We can either do a jump of length 1, a jump of length 2, or a jump of length 3, and we're going to do the 3, right? Because now we're here, meaning we're at the last position, right? We're at the last position. Therefore, we did reach the end. Therefore, we can reach the end. So we return true. Okay, so let's look at a different example. Let's look at this example. Can we determine, can we reach the last position or not, right? That's the question we are trying to answer. Let's brute force this. How can you brute force this problem? Well, let's look at every possible path we could take. So remember, we start over here. What's every single path we could take that could potentially get us to the end? If we find even a single path that can get us to our destination, then we return true. So for each of these values, I'm going to give them an index. So we know that 3 is at index 0. This is index 1, 2, 3, and 4. So these are the indices. So I'm going to start at position 0, right? We're starting at position 0 and see the value we have. The value we have is 3. That means we can make a jump of length 1, a jump of length 2, or a jump of length 3. If we make a jump of length 1, you can see we get to a 2, right? So the next position, if we took a jump of length 1, right? So from here we jump 1, then we're going to get to index 1, right? So that's what I'm going to put here. We're at index 1. If we take a jump of 2, we're obviously going to get to index 2. If we take a jump of length 3, we're obviously going to get to index 3. So these are the indices, right? So that's what each of these is representing. Each of these values is representing the index. The value on the edge here, 3, 2, 1, these are representing the jumps that we're having to take, right? We're going through all this work because we're showing the brute force solution. So from here, we're at index 1, right? We're at index 1, we have a value 2. That means we can do 2 jumps, right? A jump of 1, which would get us to index 2. So one decision is a jump of length 1, which gets us to index 2, or we can take a jump of length 2, right? Because this is a 2. So then we get to index 3, value 0. So we can take a jump of length 2 and then get to index 3. So now I'm just going to quickly start filling this tree in, and you can see that we're going to be doing a lot of repeated work, and that's what we're going to do. So this brute force solution, I think it's roughly n to the power of n, right? Where n is actually the length of our input array, right? N is the length of our input array. So this is roughly the big O time complexity of the brute force solution. I'm going to show you how to cache this, and when you cache it, you can actually make this a big O of n squared solution, but we need a little extra memory for that. But basically, we're going to optimize this brute force solution. After that, I'm going to show you the greedy solution, which is actually big O of n time complexity, and you can skip to that if you'd rather just do that. So from index 2, we see we have a value 1, right? That means we can only make 1 jump, and that jump is length 1. And when we do that, we jump from here to here, we get to index 3. Funny enough, that's where this path is also. So we're at index 3. That value is a 0 though. So what does 0 tell us? 0 tells us we can't make any jumps, right? We're making jumps of length 0, which means we're not really jumping anywhere. So basically a 3 is a dead end for us. So basically this is a dead end, right? This 3 can't lead us anywhere. And you know, now that we actually go through the rest of our tree, right? Brute force, we're going to go to this 3 and we're going to find the exact same thing is true. It can't jump anywhere. So this 3 is a dead end. This 3 is also a dead end because when we get to index 3 in our array, we cannot jump anywhere. It has a 0 value. Zeros are always going to be dead ends for us. And we actually only have one valid path left, and that's going to be from index 2. So if we were doing the brute force solution, right, which is what we've been doing up until now, creating the entire decision tree, what would we do now? We would continue the brute force right? We'd see, okay, at index 2, we have a value 1. That means we can make a jump of 1, right? And when we make that jump of 1, we get to a 3, right? We get to a 3, and we know 3s are dead ends for us, right? We cannot continue a 3 anymore, right? This is what we would do if we were doing the brute force. I'd continue, doing this part. But notice we don't actually have to do that because this is not the first 2 that we have encountered. We've already visited index 2 before. Right? Look over here, right? Here we visited index 2. And what we can do, and what we found was we actually reached the base case for that. We found that this was a trap, right? We could not reach the last index when we started at index 2, right? That's what this diagram, this decision tree tells us. When we start at index 2, we cannot reach the end. We get stuck at 3. So what we can do in our memory is DP, let's say we have an array called DP, right? That's going to be our cache. DP of index 2 is going to be false, right? That tells us we've already visited that. We've already gone down that decision before, and it's false because we could not reach the end. So now when we're over here in this position, index 2, we don't have to do anything, right? We don't have to continue that decision of making a jump of 1 and then getting to 3. We can actually immediately stop this, say, okay, no, we know that from here we cannot reach the end. And what you might have noticed by now is none of these paths can reach the end, right? So if we were doing the DP solution or a cache solution, we'd say, okay, DP of 3 is also false, of 1 is false, right? Because take a look at this 1. When you take 1, or rather this one, right? This tells us we're at index 1. Both of the paths lead to 2 and 3, and those are also false. So DP of 1 is also going to be false. And when you look at the root of this, the root tells us when we started at the first position, right? That turned out to lead to all 4 x's, right? We could not reach the end. Therefore, even when we start from the first position in this input array, we can't reach the last position. So DP of 0 is going to be false. We are going to return false, right? That's basically a little bit of the brute force solution, as well as using a cache to speed up the solution. If you do use this extra memory, this cache, you can get this solution to be O of n squared time complexity, but there's actually an even better solution. We can be greedy and we can get a linear time solution, a big O n solution. Let me show you how to quickly do that. And then the code is actually pretty short. Let's take a look. Okay, so now let's get into the actual greedy solution. So this is greedy and it's going to be linear time complexity. This problem has a pretty simple solution. We don't actually need dynamic programming. Let's look at we know that this is the starting position, right? The left or the first index is the starting position. Our goal is to get to the end position, right? But let's actually look at this in reverse order. Let's start at the end position and then see if we can work our way to the beginning in a sense, right? So in actuality, the first index is the starting position. This is the goalpost, right? This is the position that we're trying to reach. But we can see, let's work our way backwards. Let's take a look at this position. It's right next to the goal, right? This is our goal, and we're just pretend like this is a goal. So this is our goal, and this is right next to the goal. 1 means that we can make a jump of length 1. So really, we go here, we make the jump, and now we're at the goal. What does that tell us? Doesn't that tell us that we don't actually need to reach this position anymore, right? If I'm starting over here, right? Let's say we're starting over here, this guy over here can literally reach the end position, right? We know for a fact this guy can reach the end position which we're trying to reach. Doesn't that mean that we can take our goalpost and then shift it over here, right? Because we're not trying to get here anymore. Now our new goal is to get to this position because this can reach the end position, right? So from here, we're now trying to get to this position. We move the goalpost a little bit closer to us. So now we're going to put that goalpost over here. So now let's look at the next position in reverse order. So this is
Damn, why didn't I think about that? You can just decrease the size of the... I was thinking about something along the lines of that, but I couldn't... For some reason, I didn't think about that. You can just decrease the size of the list until you get to the 0 position, instead of doing the complicated thing I was trying to do.
is also a 1. That's good for us because we can make a jump of length 1 over here, right? Now, notice this guy can't reach the end position, right? Which is bad, but it can reach this position, which is where our goalpost is, which is all that really matters, right? As long as we can reach the goalpost, we can keep shifting it. So now let's shift the goalpost one more time. We can move it just a little bit closer to our initial position. Now we work our way backwards again. We're at a 3. That tells us we can make a jump of length 3 or less. So it could jump 1, 2, 3 all the way over here, right? That 3 could jump all the way to the end, which is awesome for us, but that's actually unnecessary because we see the goalpost is even closer than we expected. Now it's over here. So it can make a jump of 3 or it can make a jump of length 1. It makes no difference because either way, we can now take that goalpost and keep shifting it. So now
I guess the reason why I didn't think about that is because the problem is if you reach a 0, then you have to think about the beginning of the list, and I just didn't know how to bridge the gap between them. Because when you get to the 0 point, you're gonna have to analyze the other ones to see if you can get to them so you can skip the 0. That's the biggest problem, I think.
now the goalpost is over here. We're almost done with this problem. Now we see we're at 2. We can make a jump of length 2 or 1, and then we reach here, right? We reach the goalpost from the first position, right? Therefore, we're moving it one last time to the start position. What that tells us is, yes, we can return true because from the starting position all the way at the left, we are able to reach that end position, right? We're able to reach the last position, so we return true. And we did this in linear time because we were greedy. We kept shifting that goalpost as close as we could to us, and we don't even need extra memory for this. So that's the greedy solution, and we don't have to have a big old decision tree. We don't even need a cache or anything like that. We're literally just doing this greedy linear time with a loop. Now let me show you how to code it up. It's pretty simple. So the only main variable we really need is a goalpost, right? So initially we are going to have that goalpost or goal or whatever you want to call it at the end. So it's going to be the end, right? We're trying to reach the last index in our input array. And remember, we're going to be working our way backwards in the input array. So in Python, this is how you do it. You just take the length of the input and you can do a range loop with it. So basically what we're doing with this one line is we're starting at the last index and working our way to the beginning up until we reach the initial index, the first index. So now I want to know if we're at position I, right? I plus nums of I, right? Nums of I is going to be the jump length, right? I want to know, can this jump starting at position I, taking that maximum jump, is it greater than or equal to the goal? Because if it is, that means we can reach the goal. What do we do when we can reach the goal? we shift that goalpost even closer to us. So if we're able to reach the goal from here, we can update the goal to be I, right? I is the position that we're jumping from right now. So that's where we're going to shift the goalpost to. Awesome, right? That's literally all you have to do. Now, when we reach the end, right, either two things will be true. Either goal will now be 0, right? Meaning that from position 0, we're able to reach the goal, or goal will be greater than 0, which means we were not able to reach the end of the input list. So we can make a condition to return that. So return true, goal is equal to 0, else return false. So this is how you solve jump game in linear time with the greedy solution. No extra memory is required, and this is how you do it in Python.
Yeah, the thing is that it doesn't really explain the 0 stuff. That's the thing that was breaking my mind. That's the only thing that was stopping me from getting to this. And I still don't understand how he does. How does he deal with the 0 condition? I minus 9 minus I. Sugar. Also, he's making the size, the element in the loop, at the end of the loop, plus the number. It's very cool. He changes the goal. Yeah, but what happens when you reach 0? And then you keep moving and you don't change the goal. And then if I plus nums, yeah, but it still doesn't make sense to me. Because you can have a value that is going to be greater than the goal, and even though you can jump through that, it's not necessarily the case that you're going to be able to get to the square where you can jump through the 0. I don't really like this solution here, but I'm gonna move on to the next one. 62. And there's still 3 more that I have to do before I take a break. You're given an array of non-overlapping intervals where intervals I start end represent the start and the end of the ith interval, and intervals is sorted in ascending order by start. You're also given an new interval that represents the start and end of another interval. Okay. Insert new interval into intervals such that intervals is still sorted in ascending order by start, and intervals still does not have any overlapping intervals. As if necessary. Turn if the intervals after the insertion. Damn. I think I remember seeing this problem. Maybe I did this on Cold Wars. I think I remember seeing something similar to this. Yeah, that's... I used an object. I remember looping through a bunch of arrays, putting stuff in an object, then using the objects to find the boundaries between them. And the solution involved creating a set using iter2 combinations with a range based on the length, and then putting it to the set and returning the length of the set. So there was a similar problem to this one on Cold Wars. I just don't remember really well. And I think it's not exactly the same thing. It was a different one, but similar. So can't I compare each element of both? So loop through the first intervals and then compare Because I need to check if the interval is in between other intervals and then replace the value. So maybe the other way around. No, but then that's the problem. Because I don't necessarily want to replace on all of them. I can create a flag variable. But I still think it's gonna be off. Because it needs to be the closest one. So that's the issue. Because if I do it this way, then it's gonna replace 8 on 2 here. It's not correct. So maybe I create 2 different pointers. One starting at the end. And the other starting at the beginning. Yeah, I think that's the best way probably. So let's try that. Equals length intervals -1. Mm. Return intervals after the insertion. Okay, so let's see. So if the interval j is actually it has to be, yeah, here is 0 and then 0. I think I pressed insert by mistake. And then 1. Yeah, but there's probably some edge case that I'm missing here, I suspect. Because what if it's equal? Maybe I should put equal in the equal here. But then it wouldn't matter anyway. yeah, maybe this is the solution. So this one starts from the beginning. If the element is greater than the new interval 0, which is the smallest, then it becomes new interval 0. And I change the flag so it doesn't change any other values. And the other one starts at the end. And let's just ask. Oh, here's it should be 1. It has an integer. Oh, that should be length. Intervals. Yeah. So that's the issue. I'm changing the thing there. What if I made another condition here? Oh, so it has to be after the other one. Oh, but I should be changing the flag to false here. Oh, because it doesn't go after this. Okay. So maybe I don't need another condition. I can just do flag false. Yeah, but then the issue is that let me think. Yeah, maybe if it was 3 here and then the first one was 1, 2, then I would still need to check on the other ones. So it does need to be here, I think. So if this number so if the other one is greater than this, I just set the flag to false. Yeah, so I'm pretty much checking if it's been in between. And then I should do the same thing for the other one, probably. Just see if it's bigger. Well, let me just submit and then I think about it. 1, 2. That's another issue, is covering a whole item. Yeah, so it's a lot harder actually. Because I need to keep track of the bounds. Another thing I could do is just make this into a list. Why not? Just make intervals equal to a list with the values and then check for the boundaries and replace. Feels like it's a lot easier. And then convert to intervals again. don't understand why. It's pretty much the same thing, but no, the difference would be that how would you know how many sublists you need after the conversion? So I think I'm just gonna look at the solution. I don't want to waste a lot of time. Intervals.
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve the problem insert interval. And this is actually another problem from the blind 75 list, a list of 75 common LeetCode questions that we've been tracking on the spreadsheet. We're almost done with all of them. Today we'll be solving this interval question, insert interval. So basically we're given a set of non-overlapping intervals, and we want to insert a new interval into this list of intervals. We want the intervals to remain non-overlapping, so basically we might have to merge some intervals because we are given a single interval. We're given a list of non-overlapping intervals, in this case 2, 5. So when we insert this interval in here, you can see that 2, 5 is an interval, right? Suppose we have 1, 3, and then we have 2, 5. So clearly these two intervals overlap each other, right? So then we have to merge them together. How are we going to merge two intervals together? Well, if they are overlapping, we're going to take the minimum of both of them. In this case, it's 1, and we're going to take the maximum of both of them. In this case, it's 5. So that's what the new interval is going to be, right? So we merge them together. We'll have a new interval like this, 1, 5. And so this is a new interval. And then you can see we have another interval, 6, 9. Now, 6, 9 is not overlapping with 1, 5. So in our output now, we're going to have two intervals, right? We're going to have 1, 5 and 6, 9, and then we're going to return these intervals in the output. Now, the convenient thing is that these intervals are actually already sorted for us in ascending order based on their start times. That's good because that means we are not going to have to sort them. And if you solved any interval problems before, you know that sorting always comes in handy for interval problems. And I don't know if they specify in this problem, but just so you know, an interval such as this, let's say we had 1, 2, and another interval 2, 3, these do count as overlapping because these 2 points technically are connected. So this would be one single interval, 1, 3. I don't know if they mentioned that somewhere in the description, but that is just an edge case that we'll have to keep track of. Suppose we were given a list of intervals such as these, right? These are sorted in ascending order based on their start value. So none of these are overlapping, which is what we expect. What if we were given an interval such as this one, an interval that actually goes, let's say this is 0, right? Even though I don't know what kind of interval would end at 0, but let's just assume it is, right? So that it doesn't overlap with this one. So since even this interval, right, the end value is less than the start value of the first interval, that means this interval is not going to overlap with this interval, right? And if it's not even going to overlap with the first interval, then there's no way it could overlap with any of the upcoming intervals either, right? So when we basically return our output, we're just going to return this original list, but we're going to add this interval at the beginning, right? So that they're still in sorted order and they're non-overlapping. Now, what if the opposite was true? Suppose we were given an interval such as this one, 7 to 8 or something like that, right? Where the start value of this is actually greater than the end value of the last interval, right? In this case, this interval won't overlap with any of these, and then we can just return the original list and adding this to the end of the list, right? Now, those are a couple of the simple cases, but it's possible that the new interval could actually end up overlapping with one of these other intervals, right? And then we have to combine both of these. It could be possible that the interval actually could overlap with multiple intervals in the input, in which case we have to combine multiple intervals, right? Or it could be that the new interval would actually go somewhere in between a couple of these and not overlap at all. So how are we going to determine where exactly this new interval ends up going? Well, we'll have to iterate through these sorted intervals and then basically find the insertion point of the new interval that we're looking for. So we're going to go, suppose we have an interval like this one, right, somewhere small in between here. We're going to go interval by interval. We're going to say, okay, this is the first interval. Does this overlap with our new interval? It does not. So we would take this, add it to the output. We would look at the next, and we would see that this interval goes after that, and then we go to the next interval, and then we'd see that, okay, this next interval actually goes after the interval that we're trying to insert, right? So suppose we had a really small interval like this that goes in between. Then what would we do? Well, we wouldn't want to add this one to the result first. We would want to take this new interval, add it to the result, and then add this to the result. And then at that point, we can just take the remaining intervals and then add them to the result, and then we can return. So those are a couple more of these simple cases, right, where we would not have to merge. Suppose we had an interval such as this one, though, right? Let's say 0 to 3 or something like that. Okay, we iterate through the first interval. We see, okay, this interval is overlapping with this one. How do we know if they're overlapping or not? Well, we would check, okay, does the end value of the new interval, is it less than the start value of this interval? It's not. Okay, is the start value of the new interval greater than the end value of the current interval? It's not. So if neither of those are the case, that means this interval does not go after this interval and it does not go before this interval. So that must mean that they are overlapping, in which case we're going to merge them. How are we going to merge them? We're going to take the minimum of the left and the maximum of the right and then merge them together. So when we merge them, we're going to get a new interval such as this one, 0 to 3. And once we have this merged interval, we're not going to actually add it to the output just yet because we know that this interval could actually overlap with some other intervals that we now have that come following, right? And that's exactly the case. It's overlapping with this other interval, 3, 4. So we've gotten rid of this first interval. Now we're going to be iterating to the second interval. We're going to see 3, 4. Okay, is this overlapping with our 0, 3 interval? Yes, it is. So we're going to merge these as well. We're going to take the minimum of the left. It's going to be 0, and the maximum of the right is going to be 4. So we merge these together. So now we're going to have a new interval from 0 to 4. And we're still not going to add this to the output yet because it could technically still be overlapping with some following intervals. In this case, we're going to get to the third interval. And in this case, they're not overlapping. How do we know that? Because the end value of this one, 4, is less than the start value of the interval that we're at. So what are we going to do? We're going to take this, the first interval, add it to the result now. And then we're going to take this interval, add it to the result after it. And then we're going to go to the next interval, see that we don't have any more intervals remaining. And then we're done. So this is going to be our result in this case. 0, 4 and 5, 6 are new intervals after we've merged them and they're in ascending order. So that's kind of the general algorithm. As you can see, since it's already sorted, we'll just have to iterate through the entire list of intervals once. So the overall time complexity is going to be big O of n. That's also going to be the memory complexity if you count the memory that we're going to use to create the result array. With that being said, we can hop into the code now. But before I do, let me just give you a very quick word from our sponsor for today. If you want to get hired at top tech companies like Google, Facebook, so now let's get into the code. And so we are going to have a result of intervals. And as I mentioned, we're going to be iterating through every single interval in the input. We're given a list of intervals. They're already sorted in ascending order. So now we want to know the couple edge cases, remember? So basically, if this new interval, suppose it goes before the current interval that we're at. So suppose the end value of this new interval is actually less than the start value of the interval that we're at. So how do we get the start value? Well, interval at index I, the 0 value, this is the start value. And so basically, if the new interval has an end value that's smaller than the start value of the current interval we're at, what are we going to do? Well, that means we can go ahead and take this new interval and insert it into the result. So we'll say result.append new interval. And once we're done with that, then we basically know that all the intervals that come after it are also going to be non-overlapping, right? So we don't really have to do anything. We can just take those additional intervals, append them to the result, and then return. So in Python, an easy way to do this is result plus intervals, the sublist starting at index I going until the end of intervals, right? So we can just take that entire sublist and append it to result. You can do that with the addition operator, and then we'll just return that, right? We don't even have to continue this while loop. Now, the opposite case we discussed, remember, was else if this new interval actually goes after the current interval that we're at. Well, in that case, that means the new interval could actually still be overlapping with some intervals to the right. So we're not going to add the new interval to the result. Let me write the condition. So basically, if the new interval, the start value of this new interval was greater than the end value of the interval that we're at, then we're to the result. We're going to go ahead and append that interval that we're currently at because it's not overlapping with this new interval, but we're not going to append the new interval just yet because it could technically overlap with some additional following intervals that are coming up. And the last condition, so these two conditions are if the new interval was not overlapping, but the last condition, else, if neither of these evaluates to true, that means the new interval is overlapping with the current interval that we're iterating through. So what are we going to do? Well, we want to update the new interval in that case, right? We want to merge it with the interval that we're at. And remember, how are we going to do that? Well, we're going to take the minimum of the left value of both intervals. So this is how we can do that. The minimum of the new interval and the minimum of the current interval we're at, and the maximum of the right value of both of these. So let me copy and paste. And the right value is going to be at index 1, so we just have to change those indexes. So this is what the new interval is going to be set to. Now, once we've updated that new interval, right, we basically merged it with a different interval. Are we going to add this new interval to our result? Well, not quite, because remember, this new interval could still be overlapping with some additional intervals that are coming up. So we're not going to add it just yet. And then at the end, so once this entire loop is done executing, we're going to go ahead and return the result, right? But remember one thing. So there's two ways that we could have exited, right? One is that if we ever got to the point where the new interval was, basically if this if condition ever executed, if the new interval was not overlapping with a interval, then we go ahead and add that new interval to the result, and then we return, right? But if that never executes, then we're never going to end up adding the new interval to the result, right? So what we want to do before we return the result is go ahead and take to result.append that new interval before we return, right? Because that means basically we definitely want to append this new interval to the result, right? That's kind of what the function was telling us to do, insert the new interval. So we want to make sure that we do end up executing that. So once that's done, we have written the entire code, and as you can see, it is a pretty efficient solution. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
All right, let's go to the next one. Put a thing here. So I still have 2 more to go. I think I'm gonna take a break, and I'm probably gonna do more today. At this point, I'm just trying to finish this as fast as I can, so I can start. I think what I'm gonna do is I'm gonna read, after I'm done with this, I'm gonna read the chapter of the book for each topic that I select before moving to the next one. And yeah, I'll pick one, the first one that I'm gonna do a list ranking them to see which one I'm gonna start with, and then I'm gonna read the chapters of the book depending on which one I select. I'm gonna do that before I move to the next topic. Given an array of intervals where intervals I merge all overlapping intervals and return an array of the non-overlapping intervals that cover all the intervals in the inputs. Merge all overlapping intervals and return an array of the non-overlapping intervals that cover all the intervals in the inputs. So I have only one interval, and I need to see the ones that overlap and join them. So I'm probably gonna use a loop for this. Live. And they are all sorted. So can't I just do if intervals? Well, it's gonna be I, the first one, always, or not always, but no. So if the last one and they don't overlap, I think. So if the last of the first one is greater than the beginning of the other one, or equal to the beginning of the other one. Yeah, but how can I merge them? That's the thing. Oh, so maybe I can append and create a new one or a RAS. And I append the new one. Oh, I just realized that this one has to be 0. And then here I just append intervals. Right. So if the last element of the run, if I, that's the rows minus 1. Yeah. The only issue with this is gonna be the last element, I think. But this is probably a good start. So if the last element of the current subarray is greater or equal to the beginning element of the next array, I'm gonna append a new one. And I should probably make I plus equals 1, so it jumps the other one. So it skips the next iteration. I'm gonna append the first element of the first one with the last element of the last one. Let's save this. Oh, I forgot to return. Return RAS. And the issue is gonna be on the last list. Maybe if I do +2 here. Let's see if it changes anything. Yeah. The issue is the last one. That's the problem. Or I could just add the last one at the day on there. But it's still off here. Why is it off? Because I'm appending anyway. So, oh, obviously, else I append this. So I still have. It's because I need to increase on the other one. This one. I'm still getting the other one there. So annoying. So 3 is bigger than 2. So it's gonna append to the list 1 and 6. But then why does it? Because it should be increasing the I. There, that's the thing. Yeah, just print I here. Yeah, why is it not increasing the size of the eye? I guess it views differently the eye on the range here from this one. But if that was the case, it would throw an error here. And it's clearly going through this step here because I'm getting the 1.6 here, and here it doesn't have 1.6. So I'm not sure what's going on. Oh, maybe I can remove instead of doing this. I can just do intervals dot pop I. Alright, it should be I plus 1 actually. Or maybe both. I and I plus 1. Oh, there we go. Nice. So now all I have to do is append the last item in the end. Append intervals -1. But then, yeah. So if res -1 different, then I don't know if I can do this, but maybe I can check for the -1 1 1. Then I append. Let's see if it works on the other ones. Yeah, again the same thing. So maybe I should be popping both of them. Stop pop I. Hmm. What if I do this? Yeah. Least index out of range. I don't understand why I'm getting this. What if I do just this? Oh, it's because, yeah, I'm checking for the sublist and not the length of the thing. Yeah, this is a problem. So maybe I should perform the same check I'm doing here, but at the end there, instead of doing this. Okay, so if intervals minus 2 are equal to r to ras minus 2. Ras dot appends maybe I don't need this ras here. Or maybe I should be 0 here as well. Because I have the first one. I also don't understand why this is 0 in the beginning. It's because it's lower. Or maybe we can create an edge case when this is just equal to 2. I don't want to do this. I think I understand. I get the point. So I'm just gonna look at the solution. It's not to waste time.
Hey everyone, welcome back, and let's write some more.
Seems to be a lot easier than the other
today,
ones.
let's solve merge intervals. We are given an array of intervals with a start and an end value. So an interval is a start and an end value. You can think of it like a class or a meeting or some kind of time period or whatever. And for each of these intervals, we want to take all the overlapping intervals and then merge them. And then we're going to have a new output array of intervals. And since we merged the overlapping intervals, the result is going to be non-overlapping. So in this case, we see we have interval 1, 3 and 2, 6. So these two are overlapping. We can merge them into one interval 1, 6. The remaining two intervals are non-overlapping, so they do not get merged. And then we see that the output has 3 on intervals, one that we had to merge to get, and then the 2 original. And the second example just basically clarifies that if we have one interval 1, 4 and a second interval 4, 5, now these aren't technically overlapping in a sense, right? Like we have 1 to 4 and 4 to 5. So they clarify that these two actually do count as overlapping. So what's a good and efficient way to solve this problem? Let's say we're given the exact same 4 intervals that we were given in the original example, but notice this time they're out of order. This one is 1, 3, this one is 8, 10, this is 2, 6. It was originally over here, right? They had given the input to us in sorted order, right? So that's kind of a hint that it might be helpful for us to keep our intervals in sorted order. But what's a good way to kind of visualize what's actually going on with these intervals? These numbers are pretty descriptive, but it's better to have a picture to look at. So I'm going to draw a number line, and we're going to start at 0 because they clarify for us in the problem that any interval is not going to start at like a negative value, so we can start at 0. So let's just start putting these intervals into our number line and see what happens. So we have 1, 3, so I'm going to have a line going from 1 to 3, which is over here. So this interval is length 2. We'll have an interval going from 8 to 10, another interval of length 2. We'll have an interval from 15 to 18, and the last interval is from 2 to 6. So notice this time we actually do have an overlapping interval 2 to 6. So I'm going to draw it above. So I'm going to draw it where it's it's obvious that we have two intervals that are overlapping. Now, when you actually draw out the number line, it kind of becomes obvious that it would be very helpful for us to take these intervals and sort them based on the start value. We don't care so much about the end value because we want to go through our number line starting at the beginning, starting at the start value, going to the next start value, going to the next start value, and then continuing that, because this allows us to detect. So for example, we look at this interval first, we know it goes from 1 to 3. Next, we look at the second interval, it goes from 2 to 6. And since we just looked at the previous interval over here, we know that this one overlaps with this one. So what are we going to do? We're going to merge them together into a new interval. So it results in a new interval from 1 to 6, because remember, ultimately we are trying to merge the intervals. And then we go to our next starting position, which is 8. So we have an interval from 8 to 10, and we know it does not merge with this one because they're non-overlapping. We got some space over here, right? Lastly, we go to this interval, and it goes from 15 to 18. We know it does not overlap with this one. There's all this space in between, right? So just to reiterate, we're going to take our input list of intervals, sort by the start value of each interval, and then we're going to iterate through each start value, right? Starting at the first one, then the next one, then this one, then this one, and where each time we're going to check, okay, does the current interval, does the most recent interval overlap with the previous interval? If it doesn't, we don't do anything. If it does, which it did in this case, then we can merge them into one interval. Now, it might seem unnecessary to even have a picture like this because this interval problem is actually straightforward, right? We just sort and then we merge the intervals. But there are a lot more difficult interval problems where I'm telling you, drawing a picture like this, drawing a number line to understand what's actually going on makes the problem a lot easier to solve. So now let's write the code. Remember, we are sorting the entire input, and then iterating through the input, so the time complexity is going to be big O n log n, where n is the number of intervals that we're given. So thankfully for us in Python, it's pretty straightforward to sort. We can just take interval, sort, and what's the key we're sorting by? Because remember, we're sorting a list of pairs. So the key is going to be in Python, a lambda function. So in this case, I is going to stand for the interval. And what value of this interval are we going to use? We're going to use the first value. So at index 0, we're sorting by the start value. If we want to sort by the end value, this would be I of 1, but we're going to sort by the start value only. And so let's also declare an output where we're going to put the merged intervals. So I'm not going to initialize this to empty. I'm actually going to take the first interval and have it inserted into the output just so I can avoid an edge case. So we have initialized the interval. So now we're going to iterate through every single interval in sorted order. And technically we can skip the first one because we already added the first interval into the output. And instead of just having the interval itself, we know we're going to use the start and end value. So I'm just going to extract them like this. And so how do we know if the interval is overlapping with the most recent interval? Well, we can get from our output, this is why I added one so we can avoid the edge case. From our output, we can get the most recently added interval and get the end value of it because that's what we need to know if it overlaps. So the end value of the most recent interval, we'll call it last end. And we're going to check of the current interval we're at, the start and end value we're iterating through. If the start is less than or equal to the last ending value, that means they're overlapping. The equal is important because they told us in the second example that we are counting equal as overlapping. So if they are overlapping, what are we going to do? We're going to merge them. How do we merge them? Well, all we have to do is take the most recently added interval and take the ending value of it and set it to the max of itself, which we already have in last end, and the max of the current end value that we're at. And the reason we need to take the max is, what if we had two intervals starting at 1, 5, and the second interval is 2, 4? Because we would iterate through them in this order because this has a starting value of 1, this has a starting value of 2, but notice how this actually has a larger end value than this one. So if we just take 4 and merge this together and set this to 4, we're actually making the interval smaller. We want to keep the 5 because merging these two together is going to actually result in 1, 5. So in the case that they're non-overlapping, what are we going to do? Well, we don't have to merge, but we do have to take that interval and still add it to our output. So we're going to take start end and just add it to our output. So what would be an example of that? Well, what if we had 7, 8, right? These two intervals are non-overlapping, so the result would actually be itself, right? We don't have to make any changes. We don't have to merge. We can just leave it as it is. And that's actually it. So we didn't really have to do anything since we used the built-in sort. We took care of the main part of this problem, and all we have to do now is return the output. And so this is a pretty efficient solution. I hope this kind of explained a little bit of the intuition, and you kind of have like a visual picture of what is actually going on as we run this algorithm.
Even though this seems to be the easiest problems out of all the other ones I did so far, they are the one that I enjoy the least because it doesn't feel like I learned anything. It's just pretty much the same thing. It's just a different way. There's nothing to learn about data structures there, I think. Just a different way to use the same stuff that I was used to before to solve the problem. And the rest is just details. So I don't like these problems that much. I think I'm gonna do this one more, and then I'm gonna take a break, and then I might come back today. And if not, I'm gonna finish the list tomorrow. 64, 75. Given an array of intervals where intervals I start and return the minimum number of intervals you need to make the rest of the intervals non-overlapping. Can be removed and the rest of the intervals are non-overlapping. Intervals I should need to remove true. So yeah, I think I'm gonna look at the solution for this one. But it's pretty much just comparing, same thing from the before. You just compare the values of each one, see if they're overlapping or not. If they overlap, you remove or create a different list and then append. So it's kind of, I actually think I'm just gonna look at the solution for this one. It doesn't seem that interesting at all, to be honest. And I suspect all these intervals
Check out
problems
the
are gonna
link in the
be
description and save 10.
the same thing. So if they are like that, I'm gonna look at the solution. I don't think it's worth spending my time focusing on this. It's probably better to study more the other ones, because I'll get much more out of them than from these ones that I kind of already know the way to think about them.
% on Educative.io today. Hey everyone, welcome back and let's write some more LeetCode today. So today let's solve the problem non-overlapping intervals, and this is actually a problem from the blind 75 list of questions that we've been working on, and we've actually been tracking that list of questions on this spreadsheet. You can see that I do have a video solution on the left side over here for pretty much every single problem in this list, except for a couple that we haven't gotten to yet. So today we will be doing the last interval problem in this list. You can see I solved the other interval related problems already. There's about like 70 people viewing it right now, so I hope that you guys are finding it helpful. And you can see conveniently I made a YouTube playlist for all of the blind 75 solutions. Link to that will be in the description as well if you do want to take a look. So now let's continue with the video. So this problem is definitely like most interval problems in that if you've solved other interval problems before, this one shouldn't be too difficult, but if you're new to interval problems, this one is kind of challenging. So we're given an array of intervals where each interval has a start value and an end value, and we want to return the minimum number of intervals that we have to remove from the list to make sure that the rest of the intervals are non-overlapping. So first question you should ask is, what exactly is a overlapping interval? Well, assuming an interval looks something like this, right, it has some start value, maybe the start value is 1 and the end value is 2, right? Maybe we have another interval that starts at 3 and goes all the way to, in this case, these two is overlapping, but technically these intervals are not considered overlapping, right? So if they have the same edge point, they do not count as overlapping. This edge case is very important to understand to solve this problem. Okay, so let's take a look at the first example, actually, L3 interval. And if we have two choices for every single interval inside the list of intervals, then the time complexity to check every single possibility is going to be 2 times 2 times 2, basically 2 to the power of n, where n is the size of the input. So that's obviously not very efficient, but can we do better? And we definitely can, and it takes a greedy approach to solve this problem. When we're actually given this list of intervals, the ordering of them could be pretty random, right? But you can see when we actually draw the picture, why would we want to go through these intervals in a random order? Why would we want to look at this one, then look at this one, then this one, yeah, right? Like in just a completely random order. When you look at it this way, it kind of makes sense to want to go left to right, right? To see, okay, here are they overlapping, here are they overlapping, etc., etc. And the easiest way to do that is to iterate through them in some kind of sorted order. You can probably do it sorted by the starting point or sorted by the ending point. I'm just going to stick with sorted by the starting point, just because it's a little bit simpler for me, but I know that it works in both ways, for this problem at least. So when we iterate through these in sorted order, first we're going to compare these two intervals, right? We want to compare adjacent pairs of intervals, right? And let's actually ignore this example for just a second. Suppose we had just two intervals, right? One interval like this and one interval like this. Okay, they're in sorted order, right? And we're comparing adjacent pairs. So we're going to look at this one and look at this one. How do we know if they are overlapping? Well, if they're sorted by the starting point, we know that either they both have the exact same starting point or the second one has a starting point that's after the first one's starting point, and that's the case here. But again, how do we know if they're overlapping or not? Well, the easiest way to check is they're not overlapping if this one starts after this one ends, right? If the second one starts after the first one ends, then they're definitely not overlapping. But on the other hand, if the second one starts before the first one ends, then they're definitely overlapping, right? You can see that this is the point that they're overlapping at. Okay, so does that cover all of the cases? Well, there's one more case. Technically, that's slightly different. What if, the first one is really long and the second one starts here, right? So it does come after this one, but it ends before the first one ends. This is a slightly different edge case. Again, they are overlapping. We can detect that with the same condition. This one starts before this one ends. So yes, they're overlapping. But now, suppose we had a third interval that comes next. Remember, we are traversing these in sorted order. So first we're going to compare this one is first, this one is second. So then we're going to compare these two together. Next, are we going to be looking at this one and this one? In this case, yes. Because remember, if these two are overlapping, we don't have to remove both of them. We only have to remove one of them. So the choice is, are we going to remove this one or are we going to remove this one? Well, which one do you think we would rather remove? Would we want to remove the one that ends first or the one that ends second? Of course, we'd want to remove the one that ends first, because then there's less of a chance that it's going to overlap with the following intervals that come after. And remember, we want to minimize the number of intervals that we have to delete. In this example, with these three intervals, it doesn't matter. We could remove this one or remove this one. But let's look at another example. What if the third interval was like this, right? It's overlapping with this one. Then it becomes pretty obvious. We would want to remove this bottom interval rather than this top interval. And it depends on which one of these ends first. So that's how we're going to decide which one to remove. And just to look at a third example, so what if they were overlapping like this, right? Of course, we're going to first compare these two intervals. Okay, yes, they're overlapping, and we can detect that because this one starts before this one ends. So now we have a choice. Do we remove this one or do we remove this one? Again, we're removing the one that ends first. So we're going to remove this one, and you can see exactly why, because now these two do not overlap. But what if instead we decided to remove this one? Well, we removed it, but it didn't help us because these two are still overlapping. We want to minimize that. So basically, I just explained to you the exact algorithm that we're going to be using. We're going to sort the entire array based on the starting value, then we're going to compare adjacent pairs, and then use the conditions that I just mentioned. Now, what's the time complexity of this? Well, we're going to sort, and then we're just going to iterate through the array a single pass, right? So the iterating is simple. It's just big O of n. We're just going to iterate through the entire array. But the sorting is where the bottleneck is. So that's what the overall time complexity is going to be. Big O log. This one's, yes, they are. So they're overlapping. We're going to be using this n value to compare to the following intervals on the right side. Okay, so now let's get into everybody's favorite part, writing out the code. So remember, the first thing we want to do is sort the list of intervals. So in Python, I can just say sort, and it'll actually sort it based on the entire pair. It'll first sort it based on the start value, and then sort it based on the end value if there's a tie between the start. But, in Java and stuff, you can specify the key is just the start, or you can use just the end if you want to, and then you can slightly change your algorithm if you're sorting by the end value. But the result that we're going to keep track of is just the entire count that we have to remove. So initially, it's going to be set to 0. And remember, we're going to initially keep track of the first end value in our sorted interval. So we can get that just like this. Intervals, the first interval, and we want its end value, which is at index 1. Then we're going to iterate through the remaining list of intervals. So we can iterate through the start and end value of the remaining intervals like this. And we want to start at index 1, so we can specify specified like that in Python. And now we get to our if-else case because we want to know, are they overlapping or not? So they're not overlapping if the start value of the interval that we're looking at is greater than or equal to the previous end value. And remember, the equal is very important. That's the edge case we talked about at the beginning. If they're equal, they're technically not overlapping. And if they are not overlapping, the only thing we need to do is update our previous end, set it to the new end value, because we know that the new end value is going to be greater than the previous one. And the else case is if they are actually overlapping. And if they are overlapping, then we need to remove one of the intervals. So definitely we are going to increment our result count by 1 because we have to remove one of these. Now the question is, which one are we going to remove and how are we actually even going to handle that? Well, the only thing we actually need to update is our previous end, because remember, we don't actually have to delete the interval in the array. We just have to count how many we delete. But we do have to update the previous end. Remember, which one of these end values are we actually going to keep? Which one of the intervals are we going to keep? We're going to keep the one that has the minimum end value. So we're going to set previous end equal to the minimum of end and itself previous end. So that once we've updated this, we can use this new end value in the future iterations of the loop. But that's actually the entire algorithm. Once we've done that, we just have to return the count of how many we deleted and then run the code and make sure that it works. And as you can see, yes, it does work and it is pretty efficient. So I really hope that this was helpful. If it was, please like and subscribe. It really supports the channel a lot. Consider checking out my Patreon where you can further support the channel, and hopefully I'll see you pretty soon. Thanks for watching.
Yeah, not much to learn. And given that these other two are from the other side that I'm not gonna do, feels like I'm very close to finishing, just 8 more laps. So it's still quite a lot because I take usually half an hour for each, so 8 hours. Or actually 4 hours because there's 8, so. But I think I'm gonna stop here, and these ones are easy, so I might be able to finish them before 20 minutes. So I think I'm gonna stop here and I might come back today to keep going, try to finish today, and then if I can, it's definitely gonna be finishing this tomorrow. And I think, yeah, after I finish this, I'm gonna build the spreadsheet and decide which ones I'm gonna focus first to go very in depth into them. And then I'm gonna take a different approach. So I'll probably be back today, later on today, to keep doing this. So see you.